Okay, so last time we gave this theorem and proved it, which tells us that whenever you are given a power series, then one of the three things happens. Either the series converge at only a single point, which is x equals c, and you see from I mean the series clearly that when you plug x equals c, you get all the terms 0 except the first one. Therefore, it is clearly convergent. The second case is that the series might converge for all real numbers. And the third and the interesting case is that there is some radius, a positive number, so that the series converges for all x, so that x minus c is less than r, and diverges for all x for which x minus c larger than r. And at the endpoints, nobody knows what happens. You have to check them by hand separately. Okay, the theorem doesn't tell you anything about that. We proved this theorem, and then I guess we talked about some examples. Right. Now we will do more examples. Do you have any questions before I start regarding what we have done so far? Okay, in that case, let me just continue. Okay. Once we have this power series, you can play with them. You can apply algebraic operations to power series and operations like differentiation and integration. So first, let me mention what are the algebraic operations on power series. Okay, here is the theorem which describes how the algebraic operations are performed. So let an x to the power n, actually it doesn't have to be x to the power n. You may have this, okay, and let's say let me write it this way: bn x minus c to the power n b2 power series, b2 power series with radii of convergence uh, RA and RB respectively. So the radius of convergence of the first power series is the real number, or it can be infinite also, RA, and the radius of convergence for this one is RB. Let lambda be a constant. Then we have the followings. Then the first one is this. The power series c times a n x not c, lambda times a n x minus c to the power n has a radius of convergence RA, and as you expect, this power series lambda times a n x minus c to the power n. So you just multiply every term by a constant lambda. The expectation is that this lambda goes out, right? And it is really the case. So this is the first statement. And the second statement, okay, this is true, of course, for all x with x minus c is less than Ra. Aslında tabii bu doğru bir laf değil. Belki uç noktalarda da converge edebilir. Şöyle diyeyim. Whenever the right hand side converges. So whenever this is convergent, I have this equality. This is more than saying that it is convergent for x satisfying this, because sometimes this might converge when we have this equality, right, at the end points of the interval. So the more general statement is this. The second statement is the following. The series obtained by adding the constants of the two series has radius of convergence r at least as large as the smaller of RA and RB. Yani bu şu demek. Radius of convergence'ı bunun RA ile RB'nin minimumundan büyük veya eşit olur. And this power series is just equal to the first power series plus the second power series. Okay. All right. Where whenever both series converge. So this is true whenever both of them converge. If both series are convergent, then this is convergent and we have this equality. Okay. If you add the coefficients of a two power series, then the power series you obtained is nothing but the sum of the power series. Okay. And the proof of this is very easy. I mean, let me just write a couple of lines. So for the second one, let's say, let, for example, x in this interval, let x so that both series are convergent. X. Then, okay, now this is convergent. An x minus c to the power n. Convergent means what? The sum of the sequence of partial sums, right? Sn, which is just summation. Okay, now here this is from 0 to infinity. Sn, let's say Sn is this. Let's say k from 0 up to n. So I take first, actually n plus first terms, right? It is this one. S k, I should say. And if Rn is this one, Bn x minus c to the bk. I am sorry. I should be careful. Then okay. Şöyle diyeyim. Let diyelim. Sn ve bunlar. Then we know that both sequences Sn and Rn are convergent, right? Series are convergent means the sequences of partial sums are convergent. So Sn and Rn convergent. But if you have two convergent sequence, then Sn plus Rn, this is convergent. And what is this Sn plus Rn? Sn is this finite sum, k from 0 up to n, an x minus c to the power, sorry, ak, and Rn is this, bk x minus c to the power k. Now these are, sorry, from 0 up to n. Okay, these are two finite sums. They are not infinite sums. Since they are finite sums, I can just write it this way. So I can add these terms, ak x minus c to the power k plus bk x minus c to the power k. Okay, but this is just ak plus bk times x minus c to the power k. So this is convergent, right? This is convergent. And what is this gadget? This is just the partial sum of the series. Note that this Sn plus Rn is the nth partial sum of the series. Which series? This series. An plus Bn x minus c to the power n from 0 to infinity, right? The nth partial sum, isterseniz bunu k'li yazayım da daha şey olsun, consistent bir notasyon olsun, right? This is nothing but the nth partial sum of this series, and we know that this is convergent, therefore çok yaşa, therefore this is convergent, hence this is convergent. Is convergent, and bu neye eşit? Equals limit of Sn plus Rn, but this limit, since both of them are convergent, this limit can be written as limit of Sn plus limit of Rn, and this is nothing but lim the sum from 0 to infinity a k x minus c to the power k plus this is k from 0 to infinity bk x minus c to the power k. So this infinite sum is equal to this. You see, if you want to write the proof, proof has several steps, and it is maybe longer than you would expect. But this is the correct way of seeing why this theorem is indeed true. Okay, uh, we don't expect you to neither memorize this or understand every detail of this, but you should say some idea how we use the definitions and the proofs and the theorems we have proved so far, in theorems like this. Okay, you are just building up, the material. Okay. 29, tamam. Bir de skalerle çarptık, topladık. Bir de çarpma var, değil mi? Çarpma işinde şöyle yapıyoruz. What about product diyeyim. İki tane seri var diyelim ki elimizde. N from 0 to infinity. A n. Basitlik için böyle yapayım ama bunu x minus c diye de yazabiliriz. Right? I can write it like this, but for just simplicity, let me just write it this way. Suppose we have these two series and I want to take the product of these two. Okay, you may think it this way. If whenever this is convergent, this is equal to some function and this is equal to some function, and you are just multiplying these two functions. What will be the result? Okay, well, what is the expectation? If these were polynomials, in other words, if these were only finite sums, and from 0 to, let's say, 5, this is n equal from 0 up to 7. So degree 5 polynomial times a degree 7 polynomial. You would just multiply them, right? And you learned this in maybe elementary school, right? So you would do this: a0, a1x, a2x squared, and so on, right? And then b0, b1x, b2x squared, and so on. So what would be the result? If you multiply these two polynomials, actually they are not polynomials, right? They are infinite sums, but we may regard them as if they are polynomials. How would you multiply them? Well, you would start from the constant terms. So the constant term would be a0 times b0 plus, and then the x terms. What are the x terms? I have a0 and b1. So a0 b1 plus a1 b0, a1 b0, and I have x here. And then we have x0, sorry, x squared terms, a0 b2, a0 b2, and then a1 b1, a1 b1, and then a2 b0, a2 b0, x squared, right? And it would continue like this. Let me write a couple more terms. A0 for x cubed, the coefficient would be a0 b3, a1 b2, a2 b1, and a3 b0, x cubed, right? And it would go like this. So you see, the coefficient of x to the power 1 is what? You just multiply ai's and bj's so that the indices adds up to the power of x. Here power is 1, 0 plus 1, 1 plus 0, they are both 1. For x squared, 0 plus 2, 1 plus 1, 2 plus, it should be 0. And then for x cubed, a0, b3, a1, b2, a2, b1, a3, b0. And it will just go like this, right? And the coefficient for xn will be what? a0, bn, a1, bn minus 1. And it will go like this. This will go up to, let's say, a minus 1 and then b1. And the last term will be a0, b0, x to the power n, and so on. Okay? Well, this is just the natural product of these two objects, right? This is uh, how you would multiply them. This is called Cauchy product. This is called the Cauchy product of two series, and the theorem is this theorem. If both series are convergent, then the product series, this product series, is also convergent. I can call this gadgets, let's say this is C0, okay? Şöyle yazayım. C0 is this. This is C1, this is C2, C3, and Cn, okay? Let An, Xn, Bn, and Cn, Xn be as above, okay? Where Cn is this, A0, B1, A1, no, A0, Bn, A1, Bn minus 1, up to An, B0, okay, for all n. Then the conclusion is this. Whenever, okay, so if the radii of convergence, again, of An and Bn, Xn are Ra and Rb respectively, then the Cauchy product a Cn x to the power n has radius of convergence at least minimum of Ra and Rb, and Cn x to the power n, and from 0 to n, is equal this. Okay. So product of two series is another series, and the coefficients of the product are computed via this formula. Okay. This is just term-wise multiplication, nothing but term-wise multiplication. I will not prove this theorem because this is difficult. Okay. This would take days, I mean, for us. Okay, it is not easy, although it looks, similar to them, but it is not. This is we teach this in third year course in for math students in mathematical analysis. It requires. It is not, something too difficult to understand, but it requires a lot of machinery. So you have to build up those machinery, and it takes time. And in our course, we don't do that. In first year course, we don't do that. So just take this as granted. Okay. All right. Peki bir de integration and differentiation var. Sorusu olan var mı buraya kadar? Yani anlamadığınız bir şey olursa hemen durdurup sorun. Okay. Any questions? No questions. Okay. If there's anything you don't understand, just stop me and ask. Differentiation and integration of power series. Okay, let me just write down the theorem, and then we will do some examples and see how we use these results. If the series uh, an x to the power n, as I said, we can take it like this. Okay, let me just do it this way. If the series converges to the sum f of x on the interval, let's say minus c minus r, c plus r. So radius of convergence is r unit, and this is convergent for all x between these two numbers. And for each x, of course, you obtain a sum, and that sum, of course, will depend on the choice of x. So I can regard this power series as a function, right? For each x, you sum all these terms and you get a number. So this is a function, and whenever we have a function, we may talk about its continuity, its differentiability, its integral, and so on. And again, if this were only finite sums like this, they would be just polynomials, and we know that polynomials are differentiable and you can integrate them, right? They are integrable. You can do term-wise integration and differentiation. So the question is, can we do this if this is an infinite sum? Okay. And this theorem answers that question. So that is, yani yazdığımız şey şu. Bu ifade şuna eşit, değil mi? İşte A0 artı A1 x eksi c, A2 x eksi c'nin karesi, A3 x minus 3 cubed an x minus c to the power n, and goes like this. Okay. The conclusion is the following. Then f of x is differentiable on this interval, again c minus r, c plus r, and its derivative is just the following. You take the derivative of this as if it's a polynomial. So what is the derivative of a0? A0 is a constant. Its derivative is just 0, right? Plus derivative of this, well, it's just a1. Then derivative of this, 2 times a2 x minus c. And then derivative of the third term, 3 times a3 x minus c squared. And keep going. What is the derivative of this? It would be just n times an x minus c to the power n minus 1, and so on. Okay, so the derivative is just what you expect from the derivative, right? Uh, also f is integrable. F is integrable. Since it is differentiable, of course, it is continuous, right? Differentiable functions are continuous on this open interval. Therefore, you can talk about its integral also. And the integral uh, computed as follows: integrable over any sub-interval of minus, okay, c minus r, c plus r, and if x minus c is less than r, then we have the following. Let's say c to x f of t dt. This is nothing but, so, and from 0 to infinity. So you just take integral of this expression. What is the integral of this? You raise the power by 1 and divide by n plus 1, right? This is the integral, and this theorem tells us exactly exactly that thing. So this is equal to an over n plus 1 x minus c to the power n plus 1, or more precisely, this is a0 times x minus c, a1 over 2 x minus c squared, and then a2 over 3 x minus c cubed, and then an over n plus 1 x minus c to the power n plus 1, and so on. So you can just differentiate and integrate a power series as if it is a polynomial, okay? As if it's a finite sum. Evet. Okay. Şöyle yapayım. You choose, so we know that our power series is convergent here, and it is differentiable, and it is continuous, therefore it's integrable. So f of x is just what? It is a0 plus a1 x minus c, right? a2 x minus c squared, an x minus c to the power n. Okay? What we do, we integrate from c to x f of t dt. Okay? So this is just sorry, c to x, f is what? F of t. It is a0, a1, t minus c, a2, t minus c squared up to an t minus c to the power n, so on, and I have dt. The theorem tells us the following. Although this is an infinite sum, you can just integrate it as if it's a polynomial, as if it's a finite sum. So integral of this is what? It is just a0t, right? Integral of this one is just a1 over 2 t minus c. Okay, şu güzelce yazayım. a1 over 2 t minus c squared, a3, no, a2 over 3 t minus c cubed, and goes like this, an t minus c to the power n plus 1, and continues like this, and you uh, evaluate this at c and x, right? Sınır değerlerini koyacağız. So let's put the values. When I plug x, I get a0x and then a1 over 2 x minus c squared, a2 over 3 x, sorry, minus c cubed up to an over n plus 1 x minus c to the power n plus 1, and goes like this. And then you plug x equals c. Çok yaşa, pardon, t yerine c yazacağım. T yerine c yazarsak ne olur? So this is t equals x, t equals 0. When I plug t equals c, I get a0c, and then plus, when I plug t equals 0 here, I get 0. Bir dakika, burası da ama t eksi, neyse fark etmeyecek. Tamam, fark etmeyecek. All the other ones are 0. So what is left? I have a0x minus a0c. So this is also a0x minus c plus a1 over 2 x minus c squared, a2 over 3 x minus c cubed up to an x minus c n plus 1 and so on. Tamam mı? Bunun ispatını yapmış ama bunun ispatını vermeyeyim. Yani bence çok şey değil. Okay. Okay, there is also okay, let me bir tane daha teorem var. Onu da vereyim. Ondan sonra bol bol soru çözeriz. We have one last theorem. Theorem. Last theorem. Tabii. Abel'in teoremi de, Abel's theorem is about the convergence at the endpoints. We know that a power series has a radius of convergence, and sometimes it converges at the endpoint, sometimes it doesn't. Abel's theorem is about convergence and continuity the endpoints. This statement looks some kind of, very kind of marginal result, but this is a very important result. It's a key result in many actually applications, including of course, all kinds of mathematics, uh, probability theory in engineering. Okay, it has several applications. Theoretical parts of course, of all those studies. Uh, so you should, you know, be aware of this result. The sum of a power series is a continuous function everywhere everywhere on the interval of convergence of the series. In particular, if, let's say, an Rn converges for some r, then this function is continuous at r. Continuous means what? Limit as x goes to r from left, this summation an x to the power n is equal to an r to the power n, and if this is converges, then this limit minus r'a sağdan yaklaşırken an minus r to the power n, pardon, burası x olacak. This is equal to an minus r to the power n. Abel died at 27, but he has done so many tremendous work. After his death, people realized, how actually great his work is. And today, the most prestigious, one of the most prestigious awards in mathematics is, is the Abel Prize. So after him, actually, it is given like maybe for 20 years or so. But it's he's a great mathematician. Back then, of course, there were no antibiotics. So if you get an infection, there is no cure for it. I mean, if your body is strong, you may overcome, but otherwise you die. So that's why there are many mathematicians who died before 40 actually. One of them is also Riemann. Riemann died at 41, but you know he has done also a lot of works. So thanks to antibiotics, you know, we all actually live that long. Okay, let's give a break. After the break, I'll do examples related to all these theorems.